Good morning students. In the previous video lecture, we have discussed about the data transfer instructions available in 8085 microprocessor. In our today's video lecture, we can see about the arithmetic and logical instructions which are all available in 8085 microprocessor. Arithmetic instructions perform the operation like addition, subtraction, increment and decrement. Let us see the arithmetic instructions one by one. The first arithmetic instruction what we are going to discuss is add instruction. ADD is nothing but of the opcode for add and the operands are register or memory. While we are discussing about the arithmetic and logic unit in the architecture of 8085, I have told that the arithmetic and logic unit takes care of all the arithmetic and logical operation, and one input for the arithmetic and logic unit comes from the general purpose register, 6 general purpose register B, C, D, E and HL. So for any arithmetic or logical operation, one data comes from the register and other register or memory, and other data is from the accumulator. So for any arithmetic or logical operation, one data comes from any of the 6 register B, C, D, E, HL or from the memory, and another data is obviously from accumulator. And also I have told that after completion of this arithmetic or logical operation, the result of the arithmetic or logical operation is stored in accumulator. So after performing this arithmetic instruction, or logical instruction, the result of the arithmetic or logic instruction will be stored in accumulator, right? And again I remember that if the operand is a memory location, its address is specified by HL register pair, right? And while this arithmetic instructions are being performed, all flags are modified to reflect the result of the arithmetic and logical operation. Let us see the example for this add instruction, right? You assume that before execution the C register is holding a value 30 and A register is holding a value 20, right? And we are going to give an instruction called add C to the microprocessor. After this particular instruction add C is executed, what this add C will do, it is going to add the accumulator content with the C register content, right? Once this particular instruction add comma a register, here the register is of C is being given, means what it will do is it will take the data from accumulator and another data from the specified register. Here the specified register is C, so it will look over the C register and it will take the content of that particular register and it will perform addition on the values in accumulator and C register, and the result is being stored in the accumulator, right? So 20 plus 30 is 50 and it is being stored in the accumulator. So once we give the input value, the first input value is from accumulator and the second input value from any of the register. The next add instruction what we are going to see is add M. So one operand is of memory, it is going to reflect the HL register pair content, and that HL register pair content will be locating a memory location, right? So once add M is being given, the content of the memory location, so 2050 is holding 10 here, and the content of this memory location 10 is being added with the content of accumulator. So after execution of this instruction, what will be stored? This 10 plus 20, 30 will be stored in the accumulator. So once this instruction is executed, the arithmetic and logic unit is going to get 20 from the accumulator and 10 from the memory location 2050, and these two things are being added and it is stored in the accumulator. The next instruction what we are going to see is ADC or ADCM. ADC stands for the content of the register or memory. The content of the register or memory, and carry flag. Carry flag in the program status word or added to the content of accumulator. ADC stands for add with carry. If carry is being generated while performing any addition, that particular carry and the content of accumulator and the content of the register or memory all are being added and the result is being stored in the accumulator itself. If the operand is memory location, its address is specified by address register as usual, right? And all flags are modified to reflect the result of the addition operation. Let us see an example over here. Add C, right? ADC. ADC stands for add with carry the C register. So once this instruction is being executed, what it will do, it will take the content of accumulator, it will take the content of the specified register. Here the specified register is C, and also it will take the carry register's content. It will take the bit which is being in the carry flag, right? So all these three things are being added and the result is stored in the accumulator. You assume that before execution of this particular instruction ADCC, accumulator is holding a value of 50. C register, here since we have mentioned it as add with carry the C register is holding a value of 20, and you assume that the carry bit in the flag register is being set to 1, right? So all these three things, this 50, 20 and 1, all these things are being added and the result 71 is stored in accumulator, right? And if we see this instruction ADCM, here M is nothing but of memory. If one operand is of memory, it is going to reflect the HL register pair content, and this HL register pair content is going to locate a memory location, and that particular memory location content is added with the accumulator and carry register here. So you assume that accumulator is holding 20 and the HL register pair is holding 20 and 50. That becomes a address location in memory, and the 2050 memory location is holding 30, and carry bit in the status flag, program status flag of 8085 is set as 1. So all these three things are being added and the result is stored in the memory accumulator, and the result of this addition is going to reflect the program status word. So if we add 30 plus 20 and this one, so we will be getting 51. No carry is being obtained in this particular addition, so carry flag is cleared here. The same happens in this example also. While we add 50 plus 20, it is going plus this one, the result will be of 71. So this addition operation does not create any carry, so the carry flag is cleared after the execution. The next arithmetic instruction what we are going to see is add immediate, ADI. So similar to that of the move immediate, in move immediate what we did, we have immediately loaded a register or memory with a 8-bit data. Similarly, instead of giving the data in a particular register and to perform addition with the accumulator, what here we are going to do is we are going to immediately give the 8-bit data. This immediate 8-bit data is added with the accumulator content, and the result is stored in the accumulator, and the status flags are being affected by means of this addition operation. Let us see an example. So the example what we are going to see for this add immediate instruction is add immediate the 8-bit data which is given here. The 8-bit data given here is of 10H. So this immediate data 10 is added with the accumulator content, right? So 50 plus 10, 60. After execution of this instruction, 60 is being loaded in the accumulator. The next arithmetic instruction what we are going to see is ACI. The ACI stands for add immediately the 8-bit data along with carry to the accumulator. The 8-bit data and the carry flag are added with the accumulator content. The result is stored in the accumulator. Let us see an example for it. The example here is ACI 20, right? So what it is going to do, it is going to add this 8-bit data and the accumulator content along with the carry register content, carry bit in the program status word. So you assume that the accumulator is holding 30 before execution and carry flag is set to 1. So what it is going to do is it is going to add this 30 with the immediate given data 20 and it is going to add the carry with the result. And all these three things are being stored in the accumulator. So 30 plus 20 is 50, 50 plus the carry is of 151. This data is stored in accumulator, and while performing this particular arithmetic operation, no carry flag is being set, so the carry flag is set to 0. The next arithmetic instruction what we are going to see is DAD, right? DAD register pair. The 16-bit content of the register pair are added with the HL pair. Here in the addition operation ADD or ADC, ADI, what we did is we have did the 8-bit addition operation. If you want to perform 16-bit addition, a provision is there, an instruction called DAD is there. This DAD, direct add the 8-bit 16-bit values in the register pair. DAD, this DAD instruction what it will do is the 16-bit content of the register pair specified in the operand will be added with the HL register pair. So here while we give DAD instruction, the 16-bit values are going to come from the register pair BCDE and another value for addition is going to come from HL register pair. It is not going to come from the accumulator, because we know that accumulator is a 8-bit register and this DAD instruction is used for performing 16-bit addition operation. So one operand for this DAD instruction will come from HL register and the other value for addition can come from any of the two register pairs, remaining two register pairs, BC register pair or DE register pair. After the arithmetic operation is over, the result is stored in HL register pair, not in the accumulator, because it is a 16-bit addition. So after completion of the 16-bit addition, the result is stored in HL register pair. So while this DAD instruction is being given, the HL register pair is going to act similar to that of the accumulator in 8-bit addition, and the one 16-bit data is being coming from HL register and other 16-bit data is coming from any of the register pair. After the addition is being performed, the result is stored in the HL register pair, right? If the result is larger than 16-bit, then the carry flag is being set. Obviously, after completion of this DAD instruction, the program status word, that is the flag registers, are being modified based upon the result what is being produced by means of this instruction. Let us see an example for it. Now let us see an example for this DAD instruction. DAD D. You assume that DE register pairs are going to hold 10 and 20 and HL register pair are going to hold 20 and 50. If we specify D, then it is going to take the DE register pair here for this DAD instruction. If we specified B over here, it is going to take BC register pair, and the BC register pair content is being added with the HL register pair content. Here, since our example what we have chosen is of DAD D, it is going to choose the DE register pair content, and this DE register pair content is added with the HL register pair. Since the microprocessor 8085 microprocessor is a 8-bit microprocessor, how it will perform this 16-bit addition is it will check the least significant bit of the 16-bit number. So the least significant bits are being stored in the E register and L register for this example, right? So for this example, the least significant bits are stored in E and L register. So these two least significant bits are being chosen first by means of the microprocessor, and it is going to add this 50 and 20 first, and the result is stored in the L register, that is the least significant bit of the 16-bit, which are all being stored in the E register and L register for the chosen example is being added, and it is stored in the L register. So 50 plus 20, 70 is stored in the L register. Next, it will check, the microprocessor will check the most significant bit of the 16-bit data. The most significant bit are being stored in the H register and D register. So this 20 and 10 are added, and the result 30 is stored in the H register. While performing this addition, if a carry occurs, then the carry flag is being set to 1. If carry does not occur, then the carry flag is set to 0. Next, we discuss about the subtraction operation. Any 8-bit number or the content of the register or the content of memory location can be subtracted from the content of accumulator, as similar to that of the addition operation. In addition operation also, any 8-bit number or content of the register or memory are being added with the content of accumulator, and the result is stored in the accumulator. Similarly, while the processor is performing subtraction operation, one value will be coming from register or memory, and the other value will be coming from accumulator, and the subtraction or addition operation is being done, and the result is stored in the accumulator. Subtraction is performed in 2's complement form by means of microprocessor. If the result is negative, it is stored in 2's complement form. No two other 8-bit registers can be subtracted directly, right? Let's see the example of subtraction operation. So as we have stated that we can subtract a register with the accumulator, we can subtract a memory with accumulator, or else we can subtract the immediate data with accumulator, or we can perform subtract with borrow with the content of the specified register or with memory. We are going to see all these things as similar to that of add B, add immediate, the 8-bit data, add with memory, add with carry. Here it is of subtract with borrow, subtract with memory, right? So the first is of SUBB. SUBB, what it is going to do is it is going to subtract the accumulator content with the B register content. Here the register is of B register, so the accumulator content is subtracted with the B register content. After subtraction, the result of the subtraction is going to affect the status register or flags in the 8085 microprocessor, right? So the value 50 and 30 are chosen. For any arithmetic or logical operation, the first data will come from accumulator and the second data will be from the specified register or memory. You note this, right? So the first data will be from accumulator and the second data will be from the specified register, B register here. So 50 minus 30 is 20, that is being stored in the accumulator after the execution of this instruction. If you give SUBM, then the HL register pair content is going to act as a memory location. that memory location data is being chosen and the accumulator content is subtracted with the content of the specified memory location. So 50 minus 10, 40 is stored in the accumulator after the execution of this instruction. Next is subtract immediately the given 8-bit data. So this 8-bit data, whatever the 8-bit data which we give over here is subtracted with the accumulator content, right? You assume that the carry flag is being set before the execution, and after the execution what it will do, it will take this 50 and it will take the immediate data what the user has specified over here, and it is going to subtract these two things. So 50 minus 20 is what? 50 minus 20 is 30, and the result 30 is being stored here, and this operation is not going to provide any carry or overflow or any borrow is being generated while we perform this subtraction. So the carry flag is being set to 0. Next we see the example of subtract with borrow the register specified. So as similar to that of add with carry, what it is going to do is it is going to subtract the content of the specified register with the accumulator along with the carry register, right? So you assume that accumulator is holding 40, B register is holding 20, and the carry flag is set to 1 before execution. After execution what it is going to do is 40 minus 20, 20, we will be getting an answer of 20. 20 minus this carry bit 20, 20 minus 1 is 19. So 19 is being stored in accumulator, and while performing this SBB operation the carry flag is not set here, so the carry is cleared. And if it is of SBBM, so what it is going to do, instead of the register content it is going to choose the memory location content and it is going to subtract. So it is going to take the value 50 from the accumulator, and the memory location is of 2050. Here the 2050 memory location has a data of 10. So 50 minus 10 minus the carry flag 1. So it is of 39. The 39 is being loaded in accumulator. This subtraction operation does not contain any carry, does not produce any carry, so the carry flag is being cleared. The next arithmetic instruction what we are going to see is increment and decrement instruction. The 8-bit content of the register or memory location, the 8-bit content of the register or memory location can be incremented or decremented by 1. The 16-bit content of register pair can be incremented or decremented by 1. The increment or decrement can be performed on any register or memory, right? Let us see some examples in this increment instruction. Increment B. We are going to take an example of increment B. You assume that the B register has a content 10. Once this instruction is being executed, I have told that it is going to increment the content of B register. So 10 will be incremented as 11, right? And increment M. So if one operand is of memory, it is going to indicate the content of HL register, and that HL register content is going to mention a address location. So here it is of 2050, and 2050 is holding a value of 30. This 30 is being incremented to 1, so it will become as 31. Next arithmetic instruction is INX. The content of register pair or incremented by 1. There we have incremented the register's value. Here we are going to take the register pair. The content of register pair are incremented by 1 and the result is stored in the same place. Let us see an example for this INX instruction. So you assume that here, since we have stated that the content of register pair, so we can make use of BC register, DE register or HL register. If it is of BC register, we will be noting as INX B. Here in this example we have taken HL register, so I have written it as INX H. So the content of the HL register pair is 10 and 20. The content of HL register pair are incremented after the execution of this instruction. So 1020 is being added with 1. So 1021. So the L register content is varied and 21 is being loaded in the L register, right? The next arithmetic instruction is decrement. It is quite opposite to that of the increment instruction what we have seen. Let us directly get into the decrement instructions example. DCRE. If you give an example DCRE, there in INR the content of the specified register is incremented. If we give DCR, it is going to decrement the content by 1. So here it is mentioned as DCRE, the register is E. So the processor will look over the content of this E register, it is 20 and this is decremented by 1, that is 19 is being stored. And if it is of DCRM, so it is going to see a memory location and that memory location value was decremented by 1. Next is of DCX, as similar to that of INX, the register pair content is being decremented by 1. Let us see an example. So the example here is DCXD. So it is going to choose the DE register pair. The DE register pair's content is being decremented by 1, right? You can see the example. Now we will start discussing about the logical instructions available in 8085 microprocessor. These logical instructions perform logical operation on data stored in register, memory and status flag. The logical operations are AND, OR, XOR, rotate, compare and complement. Let me see each and every logical operation in detail now. The first logical operation what we are going to see is AND. A stands for AND, as similar to that of the arithmetic operation what we have seen. Here the microprocessor is going to perform AND operation and immediate operation, XOR operation, XOR immediately operation, OR operation, all these things. So I have given only some examples here. ANA stands for AND, XRA stands for XOR operation and ORA stands for OR operation. All these ANA, XRA operation can be done with a register, memory or it can be done immediately, right? So the first AND operation, first we are going to see about the AND operation ANA. So ANA with a register means the specified register content and the accumulator content are AND logicked. We can give a immediate data also, as similar to that of add immediate or move immediate, right? The same follows for the XOR operation or operation also. So in this example, the content of B register and accumulator content are AND logicked. Here the content of B register is 0F and the content of accumulator is AA. So the AA and 0F, the binary values of AA and 0F are being taken and the AND operation is performed, and the result after performing the AND operation, the hexa value is being stored in the accumulator. Instead of register we can give memory. If you give memory, the HL register pair content is going to locate a memory location. That location data is being taken and it is being AND logicked or XOR logicked or AND OR logicked, right? So some examples are being shown here. Next logical instruction what we are going to see is compare, right? We can compare a particular register content with accumulator, or else we can compare a memory register content with accumulator, right? Compare specified data in register or memory with accumulator. The result is stored in accumulator. Let us see some example of compare operation. Let us see some example of this compare operation. Compare D. So what it is going to do, it is going to compare the content of D register with the A register. So A register content is compared with the D register content. That is, obviously it is going to subtract. So while subtracting, we know that while subtracting or adding or doing any arithmetic operation, it is the flag registers are being affected. By means of checking over the flag, the microprocessor comes to a decision that the given number is of equal, or given number is greater, or given number is smaller, right? So here accumulator content is B8 and D register content is B9. So the B8 and B9 are being subtracted if an instruction called compare D is given. After subtraction, we know that the result of this subtraction is not of 0, so the 0 flag is cleared, and we know that the accumulator value is smaller than the D register value. As it is of smaller, then no carry is being set, so the carry is also of 0, right? And in this example, compare M, the accumulator content and the memory location content are of same. So if we subtracted, if the processor subtracted, the result is of 0, so 0 flag is offset. By means of it, the microprocessor comes to a conclusion that both the accumulator value and the memory register value are of same, right? If the accumulator value is greater than the register value or memory value, then a carry will occur. At that instant of time, carry flag will set. So by means of which the processor will come to a conclusion that the accumulator value is greater than the D register or specified register value. Next instruction is CPI. Compare immediately the 8-bit given 8-bit data with accumulator. So CPI 30, this 30, the immediate data 30 is being compared with the accumulator content, and the status flags are being affected accordingly. Next logical instruction is STC. STC is nothing but of set the carry flag. We know that by means of arithmetic and logical operation, the flags in the program status words are being setted or resetted manually. By means of giving this instruction STC, we user can set and reset a carry flag. So STC is nothing but of an instruction by means of which we can set the carry flag. We can force the carry flag to set. Once this STC is being given, the carry flag automatically is being set. Before execution, we are going to assume an example. Before execution, the carry flag is cleared. After the execution of STC instruction, the carry flag is set. Next instruction is CMC. CMC stands for complement the carry flag. We can complement the carry flag by means of this instruction. So you assume that before execution the carry flag is equal to 1. Once this instruction CMC is executed, the carry flag is complemented, so it becomes 0. The next instruction is complement accumulator, CMA. It complements each bits of the accumulator. Example is CMA. If you give CMA, what it is going to do is the accumulator content is complemented. Each and every bit in the accumulator is complemented. The next logical instruction is rotate. Rotate, RLC stands for rotate left the accumulator. Rotate left the accumulator, RLC. Rotate left the accumulator. Each binary bit of the accumulator is rotated left by one position. Bit D7 is placed in the position of D0 as well as in the carry flag. carry flag is modified according to bit D7. Let us see an example for it. So now let us see an example for this RLC instruction. It is going to rotate the accumulator content in left side direction, right? So after execution of this instruction, what happens is that each and every bit are being shifted 1 times left, right? So B7 bit comes to B0 and B0 bit moves to B1, B0 bit is going to move to B1, B2 is going to move to B3, B3 is going to move to B4, B4 is going to move to B5, B5 is going to move to B6, B6 is going to move to B7 and B7 is going to move to carry as well as to the B0 bit position. Next, RRC. RRC stands for rotate the accumulator in right side. Each binary bit of accumulator is rotated right by 1 position. Bit D0 is placed in the position of D7 as well as the carry flag. Carry is modified according to the bit D0. Let us see an example for RRC. So here the accumulator content is rotated right? So B7 bit is being moved to B6, B6 goes to B5, B5 goes to B4, B4 goes to B3, B3 goes to B2, B2 bit goes to B1, B1 bit goes to B0 and B0 bit goes to carry and B7. The next instruction is RAL, rotate the accumulator left through the carry. In the previous instruction, the carry flag is being overwritten. Now here the carry, along with the carry, the rotate operation is being performed left as well as in the right. First we will see rotate the accumulator left through carry. Example, now what happens is we are going to rotate the accumulator content left through the carry. So now what happens is the carry flag content is being moved to the B0. So the carry flag content is being moved to B0 position and B0 content, B0 bit goes to B1, B1 bit goes to B2, B2 bit goes to B3, B3 bit goes to B4, B4 bit goes to B5, B5 bit goes to B6 and B7 bit goes to carry flag, right? In the similar fashion, rotate right also happens. RAR stands for rotate accumulator right through carry, right? Let us see an example for it. Here what it is going to do, it is the B0 bit position goes to carry and the carry flag bit position is going to be placed in the B7 bit and B7 bit goes to B6, B6 goes to B5, B5 goes to B4, B4 goes to B3, B3 goes to B2, B2 goes to B1 and B0 goes to the carry. In this video lecture, we have discussed about the arithmetic and logical instruction in detail. In the next video, we can see the conditional instructions in 8085 microprocessor. Thank you.